Hello and thank you for watching my presentation. I'm very happy to participate in the ASME 2022 on my conference. Firstly, let me present myself shortly to you. My name is Manolis Annetis. I am a naval architect and marine engineer, graduated from the National Technical University of Athens. I'm currently working as a research engineer at NTUA in the research group of Professor Ventikos, the Maritime Risk Group, focusing mainly on environmental engineering, human factors, risk analysis, and maritime safety. My presentation is about the conference paper entitled A Life Cycle Cost Framework for Onboard Emission Reduction Technologies, the case of the flapping foil thruster propulsion innovation. My co-authors are Professor Nikolaos from NTUA, Professor Perera from UIT, as well as my colleagues from NTUA, Panagiotis, Sotiralis, and Eirini Stamatopoulou. In this presentation, I will shortly introduce you to the basics of our study, which is within the SeaTech project, for which I will say a few words also. Afterwards, the background of the study, including its objectives, and the methodology, namely the LCCA framework and the breakdown structure of the system considered, will follow. Finally, I will present the results, our conclusions, and the next steps of our study within the context of SeaTech project. During the past few years, but also in the decades to come, all industry sectors are trying to adapt to a new circular and sustainable economy mode in order to limit the social economic consequences of climate change. Thus, decarbonisation is crucial for all industries, and in the context of maritime industry, IMO has brought in ambitious targets toward decarbonisation in order to reduce emissions. To deal with this challenge, a variety of technological solutions are entering the industry with the aim to reduce their consumption or replace fossil fuels. Thus, SeaTech project is developing two innovations, a dual fuel engine of high efficiency and the flapping foil thruster innovation, which is also the case in this paper. In this respect, the foil thruster delivers a significant performance enhancement according to respective literature. However, this significant enhancement is mainly focusing on the performance of the foil thruster innovation without considering economic aspects. So, an LCCA framework is developed to tackle this issue and to support decision-making for the most cost-effective solution. SeaTech project has been funded under the Horizon 2020 program and aims at developing these two symbiotic innovations, the engine and the dynamic wing. It is expected to result in a 30% reduction in fuel consumption for short sea shipping cases. It had started in 2020 and will conclude in May 2023. Wärtsilä is the coordinator of the project, while other, both academia and industry partners, are completing the consortium. In respect to the foil thruster innovation, the concept is that it utilizes energy from the wave-induced motions such as pitch and converts it to useful propulsive power. This is achieved through thrust production and reduction of the ship wave resistance. It is considered to be located at the bow, where it is more efficient, in a depth around the ship's baseline and slightly in front of the hull. In extremely calm seas, the foil may increase power demand, while at rough seas, it is not safe to operate due to strength restrictions. Thus, it operates only within a range of sea states. The overall enhancement is shown to be significant by previous studies, and there is a prospect for higher levels of performance enhancement. On the other hand, life cycle approaches are very important as they provide a significant insight even from the early stages of design. They allow shifting between different configurations and alternatives in order to choose the most cost-effective solution. As life cycle approaches, LCA, life cycle assessment, is used for the environmental assessment, while the LCCA, life cycle cost analysis, is used for the economic assessment, which is the case in the present paper. The introduced LCCA framework includes the steps that are shown here. First comes the problem definition, which is defining all costs for the economic evaluation of the foil thruster installation. Then, the breakdown analysis identifies all cost elements. The first distinction of cost elements are, of course, the four life cycle phases that I will show you in the next slide. Then comes the analysis in smaller cost elements, such as the individual cost of parts and components in the construction phase. Cost modeling is the way of approximating the cost. Three models are mostly used: the analogy, parametric, and engineering models. The analogy model utilizes data from similar systems. Parametric model scales up and down the respective costs in order to approximate the cost of interest, and the engineering model is a detailed and reliable way of calculating the cost. Afterwards, all available data are collected, and then the costs are calculated in their present value in order to finally evaluate an investment regarding the foil thruster. The feedback loop that is illustrated here is very important, as it stands for the iterative process of the LCCA. According to this process, all steps should be repeated and improved due to the unavailability of data in the early stages of the product development. The gradual availability will allow more realistic and precise results. The four phases of the LCCA are shown here: construction, including retrofit costs; operation, which mainly refers to fuel consumption; maintenance, either on board or dry dock; and disposal. The right figure shows the breakdown of the cost elements. As explained earlier, the low maturity of the design, due to its high novelty, does not allow a complete analysis of all of its cost elements from early on. That is why an internal loop is created within the LCCA steps for appreciating the breakdown structure of the system, namely the foil and its retraction mechanism. Thus, the breakdown structure is continuously updated through a spiral-like model. So far, two attempts have been made to appreciate the breakdown structure of the system. The first one is a high-level approach based on a similar system, such as A-frame, cranes, or fin stabilizers. The second is a more detailed one and is based on the construction details of the small and large-scale models of the foil thruster system from within SeaTech project. Some first results for the first two attempts are presented here for the construction, maintenance, and disposal phases. All data come from literature references, industry experts, invoices, and commercially available solutions based on the cost models discussed earlier. Operation phase results are not yet mature enough, as they contain a great deal of uncertainty. Model tests will provide more reliable data and a clear picture of the foil thruster performance. To conclude, the LCCA framework is introduced to evaluate the economic performance of onboard emission reduction technologies and, in this case, the economic performance of the foil thruster innovation. It contains four phases: an iterative process to appreciate the breakdown structure of the system and the various costs, while it provides a significant insight to support decision making. These early results are formulating a threshold from the cost of construction and maintenance, as well as the benefits from the disposal phase in order for the benefits from the operation of the foil to overcome. Indicative operation phase results show a significant prospect from the economic performance of the propulsion innovation. This study, in this paper, is an early step of the LCCA, and many future steps are ahead. In more detail, we should repeat LCCA calculations with growing data availability, develop the operation phase, deal with uncertainties, consider additional costs, and of course include capital budgeting methods. Thank you very much for the attention, and my mail is available for anyone who wishes to contact me.